Hello, my name is Sean Boyle. I'm with Southern Illinois University, and today I'm going to show you guys how to use and make your own homemade vibration analyzer. And first you might ask, why do I need to make my own? There are companies that make vibration analyzers. Pico has a nice MVH kit, and within that kit they've got devices that are going to go through and allow you to synchronize data with rotating parts. And you're going to have sensors that are going to hook up to these 3-channel interface or a single channel interface, depending on what you have, so we can measure and determine the cause and the source of vibrations. And the Pico kit is really nice, but it's also pretty expensive. And it works with the Pico scope, and it also works with a pass-through device like the like a DrewTech pass-through device or the GM MDI. And it pulls vehicle information off, like engine RPM, tire size, rotations, all that kind of stuff. It calculates that for you. And that is really nice. It's very convenient, but from my opinion, from a school standpoint, I'd rather the students know how to figure all this stuff out on their own, because you're not always going to have these nice luxury tools available to you. And if you have a scope, it doesn't have to be a Pico scope. It could be an Autel, it could be a Handtech, it could be any number of digital storage oscilloscopes, and we'd still like to be able to measure and calculate our vibrations on any of those. Over the years, I've been searching for a cheap 3-axis accelerometer. Really any, it didn't have to be a 3-axis, it could just be a single-axis accelerometer. And I found from ADA Fruit, there's a company that makes a lot of parts and pieces for people who play around with Arduino stuff. You know, the little microchips where you can program things, make robots, all kinds of fun stuff. And for $16, they sell this 3-axis accelerometer. It's really cheap and it's pretty robust, and I know that because I've banged these around, and I'm pretty sure I shorted the pins on them a bunch of times, and they've never failed. They've continued to work. If you look at this chip, it's a ADXL335. Like I said, it costs about $16. You wire it up right along this section right here. You can see I got voltage in, and then that'll be 5 volts in. Then I have a ground. This 3-volt wire is just a steady 3 volts. You don't really do anything with that. Then you've got your X, Y, and Z, and then this test lead, which I don't do anything with that either. And the X-axis, Y-axis, and Z-axis are printed on that chip right there, so you can kind of get an idea of which direction they're measuring the vibration. So X would be in this direction, Y would be in that direction, and Z would be in and out like that. I also use this little 5-volt regulator. It's a simple little 5-volt regulator. You get it from digikey. And I'll put all these part numbers in the description, but these things only cost like a dollar or something. They're super cheap, or like 75 cents. And you'll see on a lot of schematics that this voltage regulator, sometimes they put capacitors on the power in and the ground. I've hooked these things up and measured them and set them with the scope, and they've got a 5-volt steady output. Really, all you have to do is put power in and a ground, and you've got 5 volts. That is how you can power these little chips up. Another thing I do when I give these little kits to my students is I give them one of these infrared phototransistors. And this little infrared phototransistor, what it does is it's an LED that is in the infrared light spectrum. And when it reflects off of something shiny, it comes back and the phototransistor picks it up and it passes current. So this is what I use to locate the position of a rotating part. So if we're measuring an imbalance in a part, like let's say a flywheel's out of balance or a drive shaft's out of balance, well, we can pick up the vibration, but we won't necessarily know where the imbalance is. So if I put a piece of little tape on the rotating part and I bring this little phototransistor up to it, on the scope I'll see a signature of when that tape passes by. It creates a little blip on the scope. You'll see that. It's really, really cool. And then the other things I send them are some resistors. We need some 10,000 ohm resistors, and because of the LED that's in here, I need a 470 ohm resistor that we put in line with the LED, so that way, because if we hook it up, it's a diode, so it'll just short through and burn the LED up. So you put a 470 ohm resistor in line. All right, so how do we wire these things up? You could see a couple versions that I've had. I'll experiment. These things, they all work, but I haven't really found a perfect way to do it. This has, I attached a little magnet, it's a little refrigerator magnet to it, and I used some hot glue, and I glued this to the magnet. What I did here for power, I just found an old USB cable, because I'm like, I just need 5 volts going to this. It's not going to draw much current. So I got an old USB cable, stripped it back, and soldered it in to my power and ground. And then I stripped a little bit of my ground lead back so I can clip my ground clamp on my scope on there. And then my other 3 leads, I just hook up to X, Y, and Z. And with it glued, I can still see the X, Y, Z on there and attach it to the part and get an idea of what I'm hooking up to. This is, it works, but one of the things that kind of sucks is if you're underneath the vehicle, you got to get your scope leads underneath and connected to this. So I've redesigned this in a couple ways. One, if I use the USB, I have to have a power supply, so I either need to plug this into the computer or have one of my USB like power packs, which is what I've been using, and it's fine. But I decided to make some others, and this one's pretty ugly, but it maybe will serve the purpose. It works great. It still works really well. I still have a magnet. This is just a transmission pan magnet, nothing exciting. Had a lot of fun with the glue gun there, just overdid it with that. I've got power and ground, and then I got my 3 axes, Z, Y, and X. I put them at different lengths so I can identify them a little bit easier. And then I got spare wire in case something breaks, but honestly I should just cut that off. So as you can see with this, I don't have a power input. So that's why, as I mentioned earlier, with the 5 volt power supply that I send with the kits here, I also give them a little battery box. And talk about ugly. This thing is really ugly. I'm not very crafty when it comes to things like glue guns and making things look pretty. I know it's extremely ugly, and but it does work, believe it or not, and everything seems to hold up. Here's the voltage regulator. I got power coming into the leg, the power in. I got ground coming out with a couple ground terminals, and I got power coming out with a couple power terminals. You'll see when we hook this up to the scope, that regulator puts out a solid, steady 5 volts without putting capacitors or anything like that in there, so it seems to work well. So this power box worked fine. It was version 1.0. I'm not going to say it got much better when I made 2.0 and 3.0, but there are things I did different. For one, I put more powers and grounds because right here as it stands, I can hook up my accelerometer and I can hook up my position sensor, but I don't have anywhere to hook anything else up, including the ground for the scope, which is important. You need to have that because if this is powering up the devices, you need the ground hooked up to the device that's powering it. So you can see with version 2.0, I made it a little different. I've got my 3 powers, and I got 4 grounds. The grounds are bare, so I can go ahead and clip a alligator clip to it. All right, now I have all these pieces and parts hooked up. I got my scope running over here. I went ahead and put the Pico scope on it. And I've got all 4 channels hooked up to it. I really don't need to do that, but just initially to show you what all we can do, I have 4 channels. I have the X, Y, and Z axis on the accelerometer hooked up, and on my position sensor, right here, I've got the signal coming into the position sensor. And as you can see, I've got my scope set up to 1 second per division. I went ahead and put channel A, B, and C. I put it on AC. And the reason why I did that is this sensor right here, it'll output like a nominal, I'm going to say around 2 volts, and then any vibration that it picks up, it's going to ride on top of that 2 volts. So I can set this up to DC 5 volts, and then I can measure the vibration or the frequency on top of that 2 volts. Or if I set the scope up to AC, it ignores the DC and just shows me any kind of oscillation or ripple. That's the reason why I see a little bit of noise up in the scope pattern, just because as it's sitting there, it's picking up any kind of electrical interference or noise, fluorescent lights, whatever we've got going on in this building. So I have my X, Y, and Z axis hooked up to the sensor, And to demonstrate this, I'm going to show you, this is attached, if you remember, to a magnet. And without getting into too much vibration theory, one thing that you might know is that everything has its own natural frequency. And I can actually demonstrate that just using this ruler. If I let this ruler hang way off the table and then I give it a flick, you can see it's going to move slow. And you can see by looking at that scope pattern, it creates a nice little oscillation. That's the frequency of this ruler dangling out 12.5 inches from the table. Really low frequency. Now if I start pulling that closer, so this is at 8 inches, you can see the frequency is a little more frequent, a little bit higher frequency. The only thing I've changed is how much of that ruler was sticking out. So now if I take this and I just barely flick it, you can see the amplitude or the strength of it is not as high. If I flick it harder, you could see the amplitude or the strength of it gets larger, but the frequency actually stays the same. Now if I shorten it up even more, so this is at 4.5 inches, you can see the frequency of the vibration is even higher yet. Actually kind of dissipates quicker. This is at 2.5 inches. So that'd create a pretty high frequency. You can see it dissipates really quick too. That's all being picked up and measured by this 3-axis accelerometer. You can see me wiggling it back and forth. It picks up that motion. $16. Now it is XYZ, so if you take a look at how I have this position on the bench, we notice that the blue line seems to be the most dramatic that changes on the scope, and that's the Z-axis. It's going up and down. If I move this side to side, you can see the green axis is the one that shows the largest strength. The blue isn't. So that is X. And if I go forward and back, you can see the red axis is what shows up the greatest, and that is the Y-axis. That's just something that if you want to, you could label it. Now, in reality, if you're picking up a lot of vibrations, you probably don't need all three. And if you have a 2-channel scope, you wouldn't be able to hook up all three. So I'm going to go ahead and disconnect 2 of them. We'll leave just the blue. Matter of fact, I'll turn that off, those others off on the scope so we don't have to look at them. The other thing we have is this position sensor. And you can see the position sensor is actually that trace up in gold. If I bring my finger close to it, you can see it changes. I've got a 10,000 ohm resistor, so I've got 5 volts going through it, and when there's a reflection, the phototransistor turns on and the voltage will drop, and I'm measuring the amount of voltage drop on the other side of that 10,000 ohm resistor. And this is using my finger, but it's really designed to pick up on something shiny. And the reflection that occurs is going to allow it to trigger back and forth. Okay, now I've got a little experiment that I'm going to do. I went ahead and made a precariously dangerous washer wedged between 2 other washers, so that way when I operate this drill, it's actually going to vibrate. It's going to spin out of balance. So this is just simulate a component that's out of balance, like on a vehicle. That's what I'm primarily going to mess with. So our accelerometer, I'm going to put on the side of the drill, just kind of hold it there, my thumb. Then I'm going to throttle the drill with my finger. You can see the scope picks up the vibration really well. Now if I take my position sensor, that is this phototransistor, and it's going to look at that reflective tape going around. You can see it does a good job of indicating the position of the drill chuck. So now if I go and stop and take a look at what I've got, you can see that the position sensor spikes down pretty much right where the upward peak is on that vibration analyzer. So the accelerometer is picking up the vibration, and the position sensor is picking up the position of the reflective tape, or the position of the drill chuck. And depending on where I have my tape in relationship to where the imbalance is, I can figure out if I'm going to add weight to it, where approximately I should add weight. Now some of these scopes have nice features, like the Pico and the Altel, where I can go through and say, all right, if that's a peak right there, then I'm going to add weight to it. Now some of these scopes have nice features like the Pico and the Altel, where I can go through and say, all right, if that's a peak right there, then I'm going to add weight to it. Now some of these scopes have nice features like the Pico and the Altel, where I can go through and say, all right, if that's a peak right there, And this is a peak right here of my vibration. And this is my location signature. And in reality, I would pick it where it drops down initially because that is going to be the beginning of the tape. Or I could do the middle if I want to just kind of reference the middle of the tape. And you can see I'm 17 degrees away from the high spot, or where the peak is at the highest amount. And that's going to be the projected weights this way, and that's where it picked it up. So that means if I were going to balance this, I'd want to put the weight on the opposite side. How much weight do you put? Well, it's kind of hard to tell. It's probably where experience would come into play. You look at the strength of the vibration, the amplitude, see how many volts basically it's generating, and once you get an idea of what's typical for your sensor, this is 138 millivolts, whatever's typical for your sensor, that's going to be an indication of how much weight you're going to add. Obviously, stronger vibrations are going to create a stronger sine wave, and it's going to be higher voltage, AC voltage, and that type of information is going to give you maybe an indication of how much weight you might want to add. Over the versions where I changed these designs, I went to this network cable because that way I can keep it long, I can go underneath the vehicle, and I can bring the cables into the vehicle where the scope leads are, and if I'm going to have to go for a drive or something like that, I don't have scope parts hanging out the window or anything like that. So if you decide to make something like this on your own, I recommend using some inexpensive long cable. There's really no current that flows through these wires to speak of, so you don't need like big thick wires or anything like that. This Cat6 network cable works pretty good. So the last part of this video is just basically going to show you how I made these sensors, and it's pretty simple. Obviously, just soldering some wires. Now the position sensor has a couple of resistors in there and a couple of connections, so that's something that you might want to pay closer attention to. And then obviously also the power supply is pretty simple. All you're doing is doing some soldering. Now I would expect you to make something better than what I've got, because I am apparently not very creative when I come up with these things. I'm cheap, so I don't want to spend a lot of money. But at the same time, I sure would hope to think that there's something better, somebody can come up with a better way to do this. And if you do, please let me know so that way I can copy your design. Okay, up here in my soldering rig, I've got 5 wires, one hooked up to the X-axis, one hooked up to the Y-out, one hooked up to Z-out, one to ground, and one to power. I'm going to go ahead and solder these on in there. At this point, my accelerometer is all soldered in there, and if I were to attach this to something, like glue it to a magnet or a clip or something like that, I can do that. Be pretty easy. This next circuit is actually a little bit more involved because I have to wire in 3 wires, but I have to add 2 resistors. And although it's not very complicated to do it, you've got to worry about these conductors all touching each other when you've got your finished product. So we'll kind of tuck some heat shrink tubing and so forth to kind of protect these circuits as I go through it. One thing that you might notice is that there's a little identification on that corner, kind of a little dot. And that identifies the location of pin number 1. So we've got pin 1 identified up here, and the reason why we need to know that is because we need to know how to wire this phototransistor up. If I label these, pin 1 is located right here, and that's actually the collector. And pin 2 is the emitter. So current flow is actually going to flow in that direction the way we're wiring it. And then the anode, let me circle that, anode is pin 3, and so current is going to flow in the direction of the diode's arrow and come out on pin 4. So those are our 4 circuits right there coming into the diode now, or the phototransistor. So I'm going to have 5 volts coming in through a 10,000 ohm resistor, and that's going to be my dropping circuit. I'm going to have another wire soldered to this, and that's going to be my signal. And then I'm going to take 5 volts and I'm going to come over to my LED. But the LED is going to have a 470 ohm circuit to limit the current flow through it. And then pins 4 and pins 2 are going to go to ground. So as you can see, I've got 3 circuits. I got signal, 5 volts, and ground. And I only need, even though I have 4 pins, I have 3 circuits because I've got 2 grounds pretty much tying into 1 circuit there. So that's why we need to know what pin 1 is, because that's where power is coming in to the transistor. And then on the opposite corner, we're going to have power coming in through a 470 ohm resistor to our diode. And then pins 2 and 4 are both grounds. Let's go ahead and provide an example of this homemade vibration analyzer. Now this vehicle right here was an SUV that had a vibration at about 22 miles an hour, and you could feel it in the steering wheel and you can also hear it a little bit. You can see I've got the scope set up at 500 millivolts per division AC, and because this was a test drive and I wanted to get as much on one screen as I could, I went ahead and set it up for 5 seconds per division. So I've actually got 50 seconds of driving on this screen. I'm going to go ahead and zoom in on this spot where it seems like the vibration's the most pronounced. And you can see the oscillations show up fairly well. One way I can determine the measurement is I could drag my rulers and just basically go peak to peak across one of these oscillations. And down here in the bottom, you could see it did the conversion for me. You might not be able to see that very well, but it says 33.33 hertz and it says 2000 RPM. So it kind of has both hertz and RPM. Another way I can check this is by just finding the section that I want to do the measurement on, kind of spanning my vertical rulers out and perform a measurement. Now I'm going to say I'm going to measure frequency between the rulers. And you can see in between the rulers here, I'm getting about 35 hertz. So the vibration's occurring 35 times per second. So on this vehicle, after doing the math, that actually came out to be about perfectly a second order drive shaft speed related vibration. The way we figured that out, and that's really a topic for a different lesson, is that we figured out how fast the tires are going at 22 miles an hour, and we multiplied that by our axle ratio, and that told us how fast the drive shaft's spinning, and it was spinning about 17 hertz, and exactly twice that is 34.5 or 35 hertz. So that basically proved that it was a second order drive shaft speed related vibration. So what was wrong with this vehicle is it had a replacement front drive shaft, and instead of having the original OE transfer case side CV joint, axle side U joint, it had a U joint placed in both sections, in the transfer case side and the axle side. Well, with that original setup, the CV joint took care of the transfer case driveline angle, and the replacement drive shaft had a U joint in that position. So there was not another U joint working at the same angle to cancel out the angle that that replacement joint was operating at, and it created a second order vibration. So we're able to pick that up with this tool fairly easily, and it pinpointed us to the right direction. Hopefully you guys get a chance to make one of these tools. Assuming you already got a scope, this is just another one of those tools that you can put in the toolbox, part of your arsenal to help diagnose vehicles that have a multitude of issues. Now you can diagnose vehicles that have vibration issues.